Hello there, students and friends. In this video, I'll be focusing only on a problem that involves elastic collision, but in two dimensions. So just relax, watch and learn. This is the problem. The attached figure shows an elastic collision, two particles, with a mass m1 equal to 0.500 kilogram, and particle B with mass m2 equal to 0.300 kilogram on a frictionless surface. Particle A has an initial velocity of 4.00 meters per second in the positive x direction and a final velocity of 2.00 meters per second in an unknown direction, alpha. Particle B is initially at rest. The question is, find the final speed of particle B and the angles alpha and beta. Okay, so as usual, we will identify the given data based from our diagram. Before the collision, we have the two particles and their individual masses. For particle A, the mass is 0.500 kilogram, while for particle B, the mass is 0.300 kilogram. All right. So the initial velocity of particle A, labeled here as v sub A1, is given, which is 4.00 meters per second, directed towards the positive x-axis, while particle B has no initial velocity, so v sub B1 is equal to 0. Now, after the collision, just after the collision, of course, the two masses are still the same, but according to the problem, the velocity or magnitude of the velocity of ball A is now reduced to 2.00 meters per second. And according to the diagram here, its direction is defined by an angle alpha that is formed, okay, by the velocity vector from the positive x-axis. So that is the angle alpha, also to be determined later on. Now, the magnitude of the velocity of particle B is also to be determined. Notice in the diagram that the arrow that represents the velocity vector for particle B makes an angle beta from the positive x-axis. In other words, we have three unknown quantities. Okay, b sub b2, which is the magnitude of the velocity of particle B just after collision, and the two angles, angle A alpha as well as angle beta. Now, how do we apply the concepts of linear momentum as well as kinetic energy? All right. So we say that the type of collision involved here is considered a perfectly elastic collision where the law of conservation of kinetic energy applies. All right. So we have here the key concept, which says that the total kinetic energy before the collision, all right, is just equal to the total kinetic energy of the two particles just after collision. Okay. The initial kinetic energy of the two particles are labeled here as K sub A1 for particle A and K sub B1 for particle B, while the kinetic energy of the two particles after collision, okay, are also labeled as Ka2 and K sub B2 respectively. for particles A and particle B, that is. And the law of conservation of momentum, okay, is also applied here, but since this involves two-dimensional collision, okay, the law of conservation of momentum is expressed in terms of the x component of the momentum as well as the y component of the momentum. All right, so for the x component, we have here the equation MA multiplied by VA1x. This is the momentum, total momentum. All right, this is the momentum of particle A before they collide. Okay, the momentum of particle B before the collision is understood to be zero, so it's no longer included in this equation. And then this is equated to the total momentum of the two particles after they collided. All right, so this is for the x component of the momenta as denoted by the subscript x. All right, for the y component, of course, the total momentum of the two particles before they collide, okay, specifically the y component is understood to be zero. All right, and that is equated to the total momentum along the y or along the y-axis for the two particles. The product of MA multiplied by BA 2y represents the momentum of particle A just after it collides with particle B. And for particle B, the momentum after collision is expressed as the product of its mass mb and its velocity after the collision, labeled as b sub b 2y. Alright, so these are the concepts that we are going to apply. In a little while, we will see how we go through with our calculations. The first step in our computation is to find the final speed of particle B, meaning the speed of particle B just after the collision. Okay, we have labeled it as b sub b2. And we use the formula for the conservation of uh, kinetic energy. All right. This equation for kinetic energy can be further expressed in terms of the formula for kinetic energy. All right. So the term on the left represents the kinetic energy of particle A before the collision. Okay. It was mentioned that the kinetic energy of particle B before they collided with particle A is equal to zero. So it's no longer written in this equation now. All right, so the right side, of course, is the kinetic energy of particle A after the collision, 1/2 mass A multiplied by speed of particle A squared. All right, this is after collision. Plus, of course, the kinetic energy of particle B, right, after the collision, expressed as 1/2 times its mass and its speed, b sub b2 squared. Then we substitute, or before the substitution, okay, we will first isolate since we are looking for b sub b2. All right. So in this equation now, we have here the transpose equation to find b sub b2. All right. Also, you will notice that there is that factor 1/2 in each term of the equation, so might as well cancel it out, all right, to further simplify our equation. So what we have here is b sub b2 squared equal to MAVA1 squared minus MAVA2 squared to be divided by the mass of particle B. Right. So the next step, of course, is to substitute each of the given quantities. All right. The mass of particle A, which is 0.500 kilogram, its speed before the collision, 4.00 meter per second, that is to be squared. Then minus the mass of particle A after the collision, its velocity is 2.00 meter per second, that is to be squared. Then divide the whole thing by the mass of particle B, which is 0.300 kilogram. Then we proceed. All right. If you're going to do your algebra, okay, you will be able to arrive at this value for B sub B2. All right. B sub B2 is already the final speed of particle B just after the collision. Don't forget that after simplifying the previous equation, there is a need for you to get the square root. All right. Because what you are looking for is B sub B2. But what we have in our equation here is B sub B2 squared. So this value of 4.47 meter per second, we say, is our final speed for particle B just after the collision. The second step in our computation is to find the angles alpha and beta. All right, so since we have two unknown variables, alpha and beta, we now apply the law of conservation of momentum considering the two components x and y. Okay, so what we have here is the equation of the conservation of linear momentum considering only the x component. Okay, so we have here, when substituted, okay, the mass of particle A multiplied by its initial velocity, all right, along the x, that is, and that is equated to, of course, the mass, again, 0.0500 kilogram multiplied by its what do you call x component of spinal velocity. All right. So since it makes an angle alpha with the horizontal, okay, that x component of its final velocity can be expressed as 2.00 meter per second multiplied by the cosine of the angle alpha. All right. And then for the last term, the x component of the what do you call this, final velocity of particle B, all right, we have the mass, which is 300 kilogram, and its x component of its final velocity, which is simply 4.47 meters per second. This was earlier calculated, all right, in step 1. And since we're referring only to the x component, then we use again cosine of the angle beta. And then again, simplifying, all right, this rather long equation, and for simplicity, okay, I do away with the units to make it look simpler. So what I have here is the product of 0.5 kilogram by the speed 4.00 meter per second. That's already now expressed as 2.00, and so on and so forth until I got this simplified equation. So again, 2.00 is equal to 1.00 multiplied by cosine alpha plus 1.34. That's the result of multiplying 0.3 by 4.47. All right. And that is to be multiplied by the cosine of angle beta. So next thing that we do is to transfer 1.34 cosine beta to the left side of the equation. So, and then the value 2.00 transferred to the right side of the equation. So, after that, the next procedure is you're going to square the whole thing. All right? Square all the terms in the equation. So the square of 1.34 is 1.80. Of course, cosine beta, the square of that is cosine squared beta, equals square of 2 is 4.00. But in squaring this right side of the equation, all right, you have to apply a mathematical rule in algebra, all right, and which will result to this, okay? When 2.00 is multiplied to 1.00 cosine alpha, okay, you are going to get negative 2.00 cosine alpha, and then you'll be doing that twice. So that's how we got minus 4, okay, 0.00 cosine alpha. And of course, the square of 1.00 cosine alpha is cosine squared alpha. All right. Then what comes after? We simply isolate cosine uh, squared beta by dividing the whole thing by 1.80. All right. So 1.80 is cancelled on this left side of the equation. We are only left with cosine squared beta. And each quantity on the right side of the equation has been divided by 1.80, resulting to 2.22 minus 2.22 cosine alpha plus 0.556 cosine squared alpha. The coefficient, numerical coefficient of cosine squared alpha is understood to be 1. And when 1 is divided by 1.80, this is how we got 0.556. All right. So, what do we do next? We label it first as our first equation. Right? Uh, we will be determining the value of the two angles, alpha and beta, okay, using two equations. All right? In algebra, if there are two unknown variables, we need at least two equations. So far, we have already one, equation number 1. So for equation number 2, we are going to show that next. All right, considering the y component for the total momentum of the two particles, okay, we have this equation. The total momentum before they collided along the y is equal to 0. Okay, but the total momentum after they collided along the y is expressed as the product of mass of particle A multiplied by its what do you call this, y component of its final velocity, plus that of particle B, which is expressed as its mass mb multiplied by the y component of its final velocity. Right? And plugging in the given data, we have 0 is equal to mass of particle A, which is 0.500 kilogram, times, all right, uh, the y component of its final velocity, which is 2.00 meter per second multiplied by the sine of the angle alpha. We use sine because we are looking for the what do you call this, the y component, all right, the y component of the final velocity, that is. And then for the y component of the momentum or final momentum of particle B, that will be equal to negative. That's why we have your minus. All right. Of course, its mass, which is 0.300 kilogram, and the y component of its final velocity, which is 4.47 meter per second, multiplied by sine of the angle beta. And simplifying, all right, doing away with the units as well, we have this more simplified equation. Now, we just transpose this term, all right, to the left side, and that is 1.34. This is the result of multiplying 0.3 by 4.47, all right? And also, uh, the product of 0.5, of course, and 2 is in fact 1. So that's how we got 1.00 sine alpha. And just like in our previous procedure, okay, the next thing that we will do is to multiply or to get the square of this equation, both sides. Square of 1.34 is 1.80, all right? Multiplied by sine squared beta. On the right side, of course, the square of sine alpha is sine squared alpha. Square of 1 is 1. And dividing both sides by 1.80 to isolate sine squared beta, we get sine squared beta is equal to 0.556 multiplied by sine squared alpha. So we say that this is our working equation number 2. Okay, earlier we already have equation number 1. Okay, and for us to be able to combine the two equations in order to determine, for example, what is the value of alpha, angle alpha, there is a need for us to apply a trigonometric identity which says that the square of the sine of angle beta plus the square of the cosine of the angle beta is equal to 1. And likewise, the other version is the square of the sine of angle alpha plus the square of the uh, cosine of the angle alpha is also equal to 1. So these two identities will be applied in determining the two angles alpha as well as beta. All right, so how do we determine the two angles, angle beta and angle alpha? All right, so we use the two equations that were earlier presented. Here they are. All right, equation 1 and equation 2. Okay, what's going to happen if sine squared beta is added to cosine squared beta? Okay, so as I was explaining earlier, uh, a trigonometry identity tells us that their sum must be equal to 1, right? So combining the two will result to a more simplified equation, which allows us also to eliminate the angle beta or the variable beta. Okay, sine squared beta plus cosine squared beta is equal to 1. And similarly, when we added 0.556 sine squared alpha, add this to what we have here in equation 1, which is also 0.556 but cosine squared alpha, what we will get is that the sine squared alpha added to cosine squared alpha is actually equal to 1. Okay? And then multiply it by 0.556 is just equal to 0.556. It is that simple. Alright? And then, what happens to the other terms? Okay? Contained in equation 1, they are just retained. That is 2.22 minus 2.22 cosine alpha. So, we are able to eliminate the first angle beta and only have here the angle alpha. In short, we can determine alpha, okay? When we proceed in our simplification, we can find alpha, okay? So, what we did was just to add this 0.556 plus 2.22, and we get 2.78. Then minus 2.22 cosine alpha. Alright? And then we will isolate 2.22 cosine alpha, okay, by moving this to the left side of the equation, and at the same time move 1 here to the right side. And what we will get is something like this. Alright? Moving 2.22 cosine alpha to the left side, okay, will give us cosine alpha, and then divide the difference between 2.78 and 1, because 1 has been transferred to the right side, making it negative, and negative 1 plus 2.78 will actually give us 1.78. Okay, and dividing the whole thing by 2.22, we now arrive at this equation, which gives us okay, the working equation in determining the angle alpha using arc cosine. I'm sure you're familiar with that, okay? With your calculator, you can now determine the value of alpha, and that is equal to arc cosine of the quotient 1.70 divided by 2.22. Using your scientific calculator, you will get this value of alpha equal to 36.7 degrees. Alright? Now, how do we determine angle beta? We can choose either equation 2 or equation 1. But we'd rather choose equation 2 because it looks much shorter and simpler. Right? So, there we go. We just substitute the angle. Alright? Sine squared beta is equal to 0.556 multiplied by the sine of the angle 36.7 degrees, and then square. You still square or get the square of the value sine 36.7 degrees before we multiply it to 0.556. Alright, so this is what comes out. The value of 36 or sine 36.7 is equal to 0.598. Get the square of that, then multiply to 0.556. Okay, and then since we are looking for sine beta, we get the square root. All right, we get the square root of 0.199. All right, and what we get is 0.446. In short, sine beta is equal to 0.446, and then using arcsine formula to get the angle beta, we now have arcsine of 0.446 to get this value of the angle beta, 26.5 degrees. All right? Now, now that we know the two angles, we also got the value of the final velocity of the lighter or the smaller particle. So by plugging in those data into the equation for conservation of momentum, okay, this is what we will get. Okay, conservation of momentum, which we earlier said that the conservation, what's this? The total momentum before they collided along the y is equal to 0. All right, this is along the y, and then that total momentum before collision must be equal to the total momentum after collision as far as the y component is concerned. Okay, so we simply substitute the given or the quantities that we have here, okay, and then simplify, and finally what we get is that this part of the equation gives us, okay, the value for the momentum Okay, the value for the momentum amounting to 0.598 kilogram meter per second. And then for the y component downward or along the negative y axis, we also get 0.598 kilogram meter per second. In other words, when you subtract them, all right, what we get is 0. So that validates our conservation of momentum, the law of conservation of momentum as applied to the y component. Okay, 0 is equal to 0. So that means our answers as far as the values of the final velocity of the lighter particle and the angle alpha as well as the angle beta, okay, we say that they are computed, okay, very accurately because when substituted, no, to one of the equations, we are able to get, okay, or we are able to satisfy the law of conservation of momentum considering the y component. So that's it. We are done with our computation for uh, a problem involving kinetic energy as well as conservation of kinetic energy and conservation of linear momentum. Okay? Thank you very much for watching. Please follow me in my FB page and please don't forget to subscribe to my YouTube channel.